The universe is described as all space, energy, and matter. Nevertheless, it's a lot more complicated than just those three simple things. When it comes to our universe, there is so much we don't understand and can't fully explain. For example, dark matter and dark energy. Both of these things are unseen but play a huge role in the expansion and development of the universe in our galaxy. Brilliant scientists over the years have all collaborated off each other's theories and ideas to come to the conclusion that the universe somehow was created 13.8 billion years ago. No one knows for sure how the universe was created. However, the leading theory most astronomers believe in is the inflation model of the Big Bang theory. At one point, everything was condensed into a singular, tiny, hot, dense point of energy. Eventually, in the blink of an eye, it got so extremely hot it exploded, followed by the expansion, creating the infinite universe as we know today. Just like if you warmed up a bowl of soup in the microwave and never stopped it, the soup would get so hot it would explode and expand all over the area of the microwave. That's exactly what is thought to have happened with the universe. However, there's nothing to stop the universe from continuing to expand. From that large, vicious explosion is where we got all of the universe's energy that will ever exist. From then on, hydrogen atoms formed together to create helium. This then would create the first stars in our galaxy. Hydrogen and helium are arguably two of the most important elements when it comes to our universe. Our sun is made out of 75% hydrogen and 25% helium, and is the center star all the planets in our solar system revolve around. Other stars would then fuse together in a proton-proton chain with other stars, creating new elements that Earth, other planets, and we ourselves are made from. The condensation theory explains how our solar system came to be. At the end of a star's life, a supernova occurs, creating iron and a few other crucial elements on the periodic table, like oxygen and nitrogen, all which are very important to the growth of life on Earth. The sun was created by a supernova, therefore when the explosion took place, a solar nebula shot out a bunch of dust and gas. These particles and debris over time slowly moved toward each other and clumped together, creating all the planets, moons, elements, meteors, asteroid belts we can see or know of in our solar system. This process didn't happen overnight. It took a vast amount of time to form our solar system. Earth has changed a significant amount since when the universe was first formed. Over 250 million years ago, you could travel from South America to Africa in a single step. Long after the Earth cooled, all of the continents of the time formed a megacontinent called Pangaea. The movement of Earth's plate tectonics is what formed this supercontinent, and is also the reason why it broke up. Continents still to this day are slowly shifting and drifting apart. In 1990, the Hubble telescope was created and we were able to see other galaxies moving away from us. In addition, we're even able to detect the acceleration of this expansion. The universe is still to this day rapidly expanding. After that hot, dense point of energy exploded, one would think after billions of years, the expansion rate of the universe would eventually slow down. In order to help us understand the workings of the universe, we came up with a standard unit system and fundamental quantities to help us grasp the mass, velocity, and acceleration of objects on our planet or in outer space. We use scalars to gain information about the magnitude of measurements, such as mass and speed, along with vectors to find the magnitude and direction of measurements, such as velocity, force, and acceleration. When it comes to force and motion, Newton breaks it down into three straightforward laws. Each of these laws, in their own way, mean the same thing essentially. The first law is known as the law of inertia. An object at rest or in motion will stay in that state unless acted upon by an unbalanced force. This law applies to objects in space and here down on Earth. The second law enlightens the relationship between acceleration and force and how the acceleration is directly proportional to its force and inversely proportional to its mass. Lastly, the third law explains how every action in force has an equal and opposite force in reaction. Overall, if you're trying to move something, you need to have an unbalanced net force in order for it to change positions from its current state. With just these three simple laws, we can calculate and predict the distance, velocity, force, and acceleration of anything on Earth or in space. Work and energy are also both significant concepts when trying to comprehend our universe's story. Work is the ability to transfer energy from one form to the next, while on the other hand, energy is the ability to do work. All the energy that we'll ever utilize was created when the hot dense point exploded up in space. Two of the most commonly known forms of energy are kinetic energy, energy in use, and potential energy, stored energy. Besides kinetic and potential energy, the other forms of energy we use are chemical, electrical, gravitational, nuclear, radiant, and electromagnetic. We use multiple types of energy each day. All sound and light found on Earth and in space transfer in the form of a wave. Sound waves are longitudinal waves that vibrate through some sort of medium such as liquid, gas, or water in order to make a sound. If a star exploded up in space, we wouldn't be able to hear it down on Earth because there's no medium for the wave to vibrate through and reach Earth. Although we can look up at the sky and see millions of stars, the light that the stars give off are electromagnetic waves, also known as transversal waves. These waves can travel through a vacuum at the speed of light. As of now, there are a total of 118 known elements on the periodic table. Stars create these elements by nuclear fusion, a reaction where small nuclei merge to form a large nucleus, while freeing energy in the process. Nuclear fission, on the other hand, is when a large nucleus splits into smaller nuclei. Both reactions, however, create enormous amounts of energy that we use every day.